There exist several methods to design IIR filters, and we will distinguish between direct and indirect methods. One direct method is pole zero placing. The general idea here is that the poles and zeros are placed directly into the Z domain, while keeping the tent plot approximation in mind in order to achieve the desired frequency response h of omega. For instance, one can place poles close to but inside the unit circle in order to achieve a passband of a filter, and zeros on the unit circle to achieve the stop end of the filter. This example here would yield a third-order low-pass filter due to the 3 poles. To increase the roll-off of the filter, the poles have to be pushed closer to the unit circle. Another direct design method is using optimization techniques. For this, one selects n data point of the desired frequency response h of omega, chooses a desired filter order, and then a least square algorithm is used to find the filter coefficients alpha and beta such that the frequency response of the filter matches the n selected data points as good as possible. Next, we will have a look at indirect methods. They all have in common that one first needs to have a suitable continuous time filter, which is then converted into the desired discrete time filter. The first method is called the finite difference discretization of differential equations. Here, the continuous time input-output equation, given by an ordinary differential equation, is discretized or approximated to yield a discrete time input-output equation, expressed as an ordinary difference equation. We have seen such an example when motivating IIR filters in the previous video. Another option is to choose the impulse invariance method, where the continuous time impulse response h of t is sampled to yield the discrete time impulse response h of k. When mapping poles and zeros, the poles PL and zeros CL of the transfer function h of s in the s-plane are converted into poles and zeros in the z-plane, where the known relationship between the Laplace transform and the z transform, namely z is equal to e to the power of s times ts, is used. The by far most used indirect design methods for IIR filters is the bilinear transform. While the finite difference discretization method aims to map the input-output equation of the CT and the DT filter, the impulse invariance method aims to map the impulse response of the CT and the DT filter, and the pole zero mapping aims to map the zeros and poles of the CT and DT filters. The bilinear transform maps the frequency range of a CT filter into the frequency range of a DT filter. We will discuss more details about the bilinear transform in the next video.